Picture this. Right now, somewhere in the darkness beyond Mars, an ancient wanderer continues its journey through our solar system. This visitor carries secrets from another star, having traveled through the cosmic void for perhaps millions of years before arriving at our doorstep. 3. I/ATLAS represents something extraordinary in human experience. It's only the third confirmed interstellar object we've ever detected, a cosmic messenger that originated not from our solar system, but from the vast spaces between the stars. When it was discovered in July 2025, astronomers immediately recognized its alien signature, a hyperbolic trajectory that could only mean one thing. This object came from somewhere else entirely. The journey that brought 3 I/ATLAS to us defies human imagination. While we measure our longest voyages in decades, this visitor has been traveling for geological ages. It has witnessed the birth and death of stars, survived radiation that would instantly destroy any earthly organism, and endured temperatures just above absolute zero. Yet here it is, racing through our cosmic neighborhood at over 200,000 kilometers per hour. What makes this visitor particularly fascinating is its size and composition. Estimates suggest 3 I/ATLAS stretches several kilometers across, large enough to contain entire cities, yet small enough that its presence goes unnoticed by anyone not specifically looking for it. Its surface likely bears the scars of its interstellar journey: cosmic ray impacts, chemical alterations from eons of radiation exposure, and the deep cold that comes from traveling in the space between worlds. The real 3 I/ATLAS follows a safe path through our solar system. Its closest approach to the Sun places it roughly between Earth and Mars orbits, far enough away to pose no threat to our world or any other. This is important to understand because what we're about to explore together is purely hypothetical. We're embarking on a thought experiment, asking what would happen if this interstellar visitor's path were different. Scientists love thought experiments because they help us understand the fundamental forces that govern our universe. By imagining scenarios that push physics to its limits, we gain insights that would be impossible to achieve through direct observation. Tonight, we'll use 3 I/ATLAS as our guide into one of the most extreme environments imaginable, the heart of our solar system's nuclear furnace. The Sun dominates our cosmic neighborhood with such overwhelming power that it's difficult to comprehend. Every second, it converts 4 million tons of matter into pure energy, releasing more power than humanity has used throughout its entire history. Into this inferno of nuclear fusion and magnetic chaos, we'll imagine our interstellar visitor falling, carrying with it the frozen chemistry of another star system. This journey will take us through multiple layers of scientific understanding. We'll explore what happens when matter from one star system encounters the plasma environment of another. We'll witness the transformation of ancient ice into superheated gas, and we'll discover why even the largest cosmic projectiles are essentially insignificant when measured against stellar forces. But more than that, we'll gain perspective on the true nature of our cosmic environment. The universe operates on scales so vast that our everyday experience provides few useful analogies. Through this exploration, we'll develop an intuitive understanding of stellar physics, interstellar chemistry, and the delicate dance of forces that keeps our solar system stable and predictable. Our interstellar visitor awaits, carrying its cargo of alien ice toward an imaginary appointment with the Sun's nuclear heart. Before we imagine 3 I/ATLAS plunging into our Sun, we must first appreciate the extraordinary voyage that brought it to our solar system. This journey represents one of nature's most remarkable survival stories, a tale of endurance that spans distances so vast they challenge human comprehension. When 3 I/ATLAS began its interstellar journey, our solar system likely didn't exist in its current form. Earth was either a molten ball of rock or perhaps not yet fully assembled from the cosmic debris surrounding our young Sun. The visitor we're studying tonight has been traveling through space longer than complex life has existed on our world. The environment between stars is hostile beyond anything found on Earth. Space is not truly empty. It's filled with radiation, magnetic fields, and occasional atoms of hydrogen drifting in the cosmic wind. For an object like 3I/ATLAS, this journey meant constant bombardment by high-energy particles capable of breaking apart molecular bonds and altering chemical structures at the atomic level. Imagine the coldest place you've ever experienced, then make it hundreds of degrees colder. Interstellar space hovers just a few degrees above absolute zero, the theoretical temperature where all atomic motion stops. In this environment, the ice that makes up much of 3I/ATLAS's composition becomes harder than steel, preserving chemical signatures from its birth system like a cosmic time capsule. The radiation environment tells another story of survival. Cosmic rays, high-energy particles accelerated by stellar explosions and magnetic fields, constantly pepper any object traveling through interstellar space. Over millions of years, this radiation acts like a cosmic sandblaster, slowly eroding surfaces and creating chemical changes that transform the original composition. The fact that 3I/ATLAS still contains identifiable ices suggests remarkable structural integrity. Perhaps most remarkably, our visitor has navigated the gravitational landscape of our galaxy without being captured by any other star system. The Milky Way contains roughly 400 billion stars, each one exerting gravitational influence that extends far beyond its visible boundaries. For 3I/ATLAS to reach us, it must have threaded a cosmic maze of stellar gravity wells, each encounter potentially altering its trajectory or even capturing it entirely. The speed at which 3I/ATLAS travels tells us about the violence of its origin. Objects don't achieve interstellar velocities through gentle processes. Something dramatic ejected this visitor from its birth system. Perhaps a gravitational encounter with a giant planet, the explosion of a nearby star, or the chaotic dance of multiple stellar bodies in a young star cluster. This ejection velocity has remained essentially unchanged throughout the entire journey. Unlike objects in our solar system that speed up and slow down as they orbit the Sun, interstellar visitors maintain constant velocity relative to the galaxy itself. This constancy provides crucial clues about where they came from and how long they've been traveling. What emerges from this impossible journey is an object fundamentally different from anything native to our solar system. 3I/ATLAS carries chemical signatures from an alien star, surface modifications from cosmic radiation exposure, and structural properties shaped by millions of years in the deep cold of space. It's a sample of another world delivered to our cosmic doorstep. The fact that we can detect and study such objects represents a revolution in our understanding of galactic chemistry and planetary formation. Each interstellar visitor is like receiving a laboratory sample from a star system we'll never visit directly. This remarkable journey sets the stage for our hypothetical scenario. An object that has survived the impossible voyage between stars now faces the ultimate test, an encounter with the nuclear furnace at the heart of our solar system. Throughout history, humans have witnessed spectacular cosmic collisions that illuminate the fundamental forces governing our universe. Long before we understood the physics involved, ancient astronomers recorded guest stars that appeared suddenly in the night sky, blazing brightly before fading away. Today, we know these were often the result of material falling into stars or stellar explosions triggered by cosmic encounters. Our modern instruments have captured events that dwarf human imagination. In 2013, comet ISON approached the Sun on what many thought would be its final orbit. Astronomers worldwide watched as this dirty snowball, roughly a kilometer across, raced toward our star at incredible speeds. The comet began disintegrating while still millions of kilometers away, torn apart by solar radiation and tidal forces long before it could reach the Sun's visible surface. The physics of star-comet encounters operates on scales that challenge our intuitive understanding. Stars are not solid objects like planets. They're vast spheres of plasma held together by their own gravity. The the Sun's surface is actually just the layer where the star becomes opaque to visible light. Above this photosphere lies the corona, a region of superheated gas extending millions of kilometers into space, with temperatures reaching several million degrees. When comets approach the Sun, they encounter increasingly hostile environments at each stage of their journey. The first casualties are the most volatile ices, frozen gases that sublimate directly from solid to vapor as solar radiation intensifies. This process creates the magnificent tails we associate with bright comets, streams of gas and dust pushed away from the Sun by radiation pressure and solar wind. Comet Lovejoy provided a stunning example in 2011 when it appeared to survive a close solar encounter, diving to within 140,000 kilometers of the Sun's surface. For hours, the comet vanished from view, hidden in the solar glare. When it emerged, astronomers were amazed to see a surviving nucleus, though dramatically smaller and altered by its fiery passage. These observations reveal the incredible energy densities near stars. The Sun outputs roughly 380 trillion watts of energy continuously, equivalent to detonating 100 billion nuclear weapons every second. Against such overwhelming power, even massive comets appear insignificant. The energy contained in a kilometer-sized comet, if converted entirely to light and heat, would power the Sun for perhaps a few microseconds. The spectacle of solar encounters extends far beyond the visible destruction. When cometary material vaporizes in the solar atmosphere, it creates distinctive spectral signatures that reveal the chemical composition of the falling object. Astronomers can identify elements and compounds that originated in completely different stellar environments, reading the chemical history of alien worlds in the light of their destruction. Solar observing spacecraft have revolutionized our ability to study these events. The Solar Dynamics Observatory, the Solar and Heliospheric Observatory, and other missions provide continuous monitoring of our star's activity. These instruments can track objects as they approach the Sun, documenting the progressive heating and disintegration in exquisite detail. The magnetic environment around stars adds another layer of complexity. The Sun's magnetic field is incredibly powerful, capable of accelerating particles to enormous speeds and shaping the flow of solar wind throughout the solar system. When foreign material enters this environment, it interacts with magnetic field lines in ways that can be observed from Earth. What these encounters teach us extends beyond the fate of individual comets. They provide laboratories for studying extreme physics, stellar atmospheric properties, and the behavior of matter under conditions impossible to recreate on Earth. Each collision offers insights into stellar structure and the fundamental processes powering our Sun. This background prepares us for understanding what might happen if 3I/ATLAS, with its unique interstellar chemistry and million-year journey, were to encounter our star directly. Before we embark on our journey of imagination, we must be absolutely clear about one crucial fact. 3I/ATLAS will not hit the Sun. The real trajectory of this interstellar visitor carries it safely through our solar system, passing closest to our star at a distance of roughly 1.4 astronomical units, placing it somewhere between the orbits of Earth and Mars. This is important scientific truth, and we must never lose sight of it. What we're about to explore together is a thought experiment, a what-if scenario that scientists use to better understand the physical processes governing our universe. By imagining extreme situations, we can push our knowledge to its limits and gain insights that would be impossible to achieve through direct observation alone. Think of thought experiments as mental laboratories where we can safely explore dangerous or impossible scenarios. Einstein used thought experiments to develop his theories of relativity, imagining what it would be like to ride on a beam of light or fall freely in an elevator. These mental exercises led to revolutionary insights about space, time, and gravity. In our case, we're asking what would happen if 3I/ATLAS's trajectory were different. Instead of its safe path through the outer solar system, imagine if some cosmic accident had nudged it onto a collision course with our Sun. Perhaps a gravitational encounter with an unseen object, or a small course correction that accumulated over millions of years of interstellar travel. This hypothetical scenario allows us to explore several fascinating areas of physics simultaneously. We'll investigate how interstellar material behaves in extreme stellar environments, understand the incredible energy scales involved in solar physics, and appreciate the delicate balance of forces that keeps our solar system stable and predictable. The value of such speculation extends beyond mere curiosity. Throughout history, thought experiments have led to practical discoveries and technological innovations. By understanding what happens when matter encounters extreme conditions, we develop better models for stellar evolution, planetary formation, and even the behavior of material in laboratory fusion reactors. Our imaginary collision also provides a unique perspective on the nature of interstellar objects themselves. 3. I/ATLAS carries chemical signatures from another star system, preserved in ice that has remained unchanged for millions of years. What would happen when this alien chemistry encounters the nuclear furnace of a different star? The answer reveals fundamental truths about the universality of physics and chemistry across the galaxy. The scenario we're exploring has precedent in the real universe. Astronomers have observed similar events around other stars where comets and asteroids fall into stellar atmospheres. These observations provide the scientific foundation for our speculation, grounding our imagination in established physics rather than pure fantasy. It's worth noting that such events, while dramatic from our perspective, are relatively common in cosmic terms. Every star system likely experiences periodic bombardment by interstellar objects, though most are far too small and distant for us to observe. Our Sun has probably encountered numerous interstellar visitors throughout its 4.6 billion year history. The intellectual framework we'll use combines observational astronomy, laboratory physics, and theoretical modeling. We'll draw on decades of solar research, comet studies, and high-energy physics to construct a scientifically plausible narrative of destruction and transformation. Most importantly, this thought experiment helps us appreciate the incredible scales and energies involved in stellar processes. By following 3 I/ATLAS through its hypothetical final moments, we'll develop an intuitive understanding of why stars dominate their environments so completely, and why even large cosmic projectiles have virtually no effect on stellar behavior. Our journey begins with understanding, proceeds through imagination, and concludes with deeper appreciation for the cosmic forces that shape our universe. To understand what would happen if 3 I/ATLAS encountered our Sun, we first need to appreciate the incredible scales involved in this cosmic drama. The universe operates on dimensions so vast that our everyday experience provides few useful comparisons, yet grasping these scales is crucial for understanding the physics of stellar encounters. 3 I/ATLAS stretches roughly 3 to 6 kilometers across its longest dimension, making it comparable in size to a large city. If you could place it next to Manhattan, it would span from the southern tip of the island well into the Bronx. This is substantial by human standards, yet in cosmic terms, it's barely a speck of dust. The composition of our interstellar visitor adds another layer to its story. Unlike the rocky asteroids native to our solar system, 3 I/ATLAS consists largely of ices, frozen water, carbon dioxide, and various organic compounds that condensed from gas around another star billions of years ago. These ices are not soft like those in your freezer. After millions of years in interstellar space, they've been compressed and hardened by cosmic radiation into materials tougher than concrete. To put this in perspective, imagine 3 I/ATLAS as a frozen mountain, carved from the chemical debris of an alien world and hurled across the galaxy by forces we can barely comprehend. Its mass likely ranges from hundreds of billions to trillions of kilograms, equivalent to thousands of the largest ships ever built by humanity. Now consider our Sun, a sphere of plasma and nuclear fire stretching 1.4 million kilometers in diameter. If Earth were a marble, the Sun would be a sphere nearly 4 meters across. The scale difference between 3I/ATLAS and our star is similar to comparing a grain of sand to a basketball, except even this analogy understates the true disparity. The Sun's mass dwarfs everything else in our solar system combined. It contains 99.86% of all the matter orbiting in our cosmic neighborhood, with all the planets, moons, asteroids, and comets representing barely 0.1% of the total. Against this overwhelming bulk, 3I/ATLAS becomes essentially massless. But mass tells only part of the story. The Sun is not a cold, solid object like a planet. It's a fusion reactor operating at temperatures and pressures that turn matter into plasma, a fourth state of matter where electrons are stripped from atomic nuclei. The Sun's core reaches 15 million degrees Celsius, hot enough to fuse hydrogen into helium and release the energy that lights our solar system. The energy output reveals the true scale of stellar processes. Every second, our Sun converts 4 million tons of matter directly into energy through nuclear fusion. This is equivalent to detonating billions of nuclear weapons continuously, yet the Sun has been maintaining this rate for over 4 billion years and will continue for billions more. When we compare 3I/ATLAS to objects that have actually encountered the Sun, the perspective becomes even more striking. Comet Ison, which disintegrated during its 2013 solar approach, was roughly half the size of our interstellar visitor. Comet Lovejoy, which survived its 2011 encounter, was even smaller. The fact that these much smaller objects were completely transformed by solar energy gives us insight into what awaits anything larger. The chemical composition of 3I/ATLAS makes it particularly vulnerable to solar heating. Ice sublimates directly from solid to gas when heated, creating enormous volumes of vapor from relatively small amounts of solid material. A cubic kilometer of ice can produce billions of cubic kilometers of gas when vaporized, and 3I/ATLAS contains several cubic kilometers of the most volatile ices known. Understanding these scales prepares us for the physics of destruction that would unfold if our interstellar visitor were to fall toward the Sun. Size, composition, and energy scales combine to determine the fate of any object entering the solar environment. Long before 3I/ATLAS could reach the Sun's glowing surface, it would encounter layers of increasingly hostile environment that extend far beyond what our eyes can see. The Sun is not simply a bright disk in the sky. It's surrounded by an invisible atmosphere that reaches across millions of kilometers, creating a gauntlet of extreme conditions that would begin destroying our interstellar visitor while it's still farther from the solar surface than Earth is from our moon. The outermost layer of this invisible shield is the heliosphere, a vast bubble of solar influence extending beyond the orbit of Pluto. Within this region, the Sun's magnetic field and particle emissions dominate the local space environment. For 3I/ATLAS, entering the heliosphere would mark the beginning of its transformation from interstellar wanderer to solar casualty. As our visitor travels deeper into the Sun's domain, it encounters the solar wind, a continuous stream of charged particles flowing outward at speeds exceeding 1 million kilometers per hour. This wind carries magnetic field lines that can accelerate particles and strip away the outer layers of any object entering the solar environment. The same force that creates comet tails would begin working on 3I/ATLAS, though initially at levels too subtle to detect. Moving inward, we reach the corona, perhaps the most mysterious and violent region of the solar atmosphere. Paradoxically, the corona is hundreds of times hotter than the Sun's visible surface, reaching temperatures of several million degrees. This superheated plasma extends roughly 2 solar radii from the Sun's surface, creating a region where matter exists in conditions impossible to replicate on Earth. The physics of coronal heating remains one of solar science's greatest mysteries. Somehow, energy from the Sun's surface is transported upward and converted into the kinetic energy of particles moving at incredible speeds. Magnetic field lines twist and reconnect explosively, releasing energy equivalent to millions of nuclear weapons in events called solar flares. For an object like 3I/ATLAS entering the corona, the environment becomes immediately lethal. The temperature alone would begin vaporizing surface materials, but the corona also contains magnetic fields powerful enough to accelerate charged particles to near-light speeds. Any material stripped from our visitor would be caught up in this magnetic chaos, twisted and accelerated by forces beyond earthly comprehension. Below the corona lies the transition region, a thin layer where temperature drops rapidly from millions of degrees to mere thousands. This boundary marks the edge of the sun's visible atmosphere, where the physics change from plasma processes to more familiar gas behavior. The transition region is where most of the sun's ultraviolet radiation originates, energy capable of breaking apart molecular bonds and ionizing any remaining atoms. Finally, we reach the chromosphere, a layer of relatively cool gas that gives the sun its characteristic red color during eclipses. Even here, temperatures exceed 4,000 degrees Celsius, hot enough to vaporize any known solid material instantly. The chromosphere extends roughly 2,000 kilometers above the photosphere, creating a final barrier of superheated gas. These atmospheric layers work together as a defensive system that would dismantle 3I/ATLAS piece by piece, starting from its outer surface and working inward. The process begins with sublimation of the most volatile ices, continues through the breakdown of molecular structures, and culminates in the complete ionization of all atomic material. Understanding these invisible shields helps us appreciate why reaching the sun's actual surface is nearly impossible for any comet or asteroid. The journey through the solar atmosphere is like trying to reach the bottom of an ocean of fire, where each kilometer of descent brings exponentially more hostile conditions. The stage is set for 3I/ATLAS's hypothetical encounter with forces that dwarf anything experienced during its million-year journey through the cold darkness between stars. As 3I/ATLAS begins its hypothetical fall toward the sun, the laws of physics transform our interstellar wanderer into something resembling a cosmic bullet, accelerating to speeds that would make its already impressive interstellar velocity seem leisurely by comparison. This acceleration tells a story of gravitational forces so powerful they dwarf human experience, yet follow the same fundamental principles that govern a falling apple. When 3I/ATLAS first enters the sun's gravitational influence, it's already traveling at roughly 60 kilometers per second relative to our star. This speed alone represents energies beyond earthly comparison, but it's only the beginning. As gravity pulls our visitor deeper into the solar system's heart, its velocity increases dramatically with each passing kilometer. The physics governing this acceleration are elegantly simple yet profound in their implications. Every object near the sun experiences gravitational acceleration of roughly 274 meters per second squared at the solar surface, about 28 times stronger than Earth's gravity. For an object falling from the outer solar system, this acceleration compounds continuously, transforming orbital energy into kinetic energy according to the fundamental laws of conservation. By the time 3I/ATLAS reaches the orbit of Mercury, roughly 58 million kilometers from the Sun, it would be traveling at approximately 200 kilometers per second. This represents a fourfold increase over its initial interstellar velocity, achieved through the inexorable pull of solar gravity, working across vast distances. The energy involved becomes staggering when we consider the mass of our visitor. Every kilogram of 3I/ATLAS material would carry kinetic energy equivalent to several tons of chemical explosives. Multiply this by the trillions of kilograms in our hypothetical impactor, and the total energy approaches that released by nuclear weapons, yet this energy is entirely gravitational in origin. As 3I/ATLAS continues inward, passing the orbit of Venus and then Earth, its speed climbs toward 400 kilometers per second. At this velocity, our visitor would cross the distance from New York to Los Angeles in roughly 10 seconds. The material of 3I/ATLAS is now moving so fast that relativistic effects begin to become measurable, though still small compared to the total energy involved. The final acceleration phase occurs within the last few million kilometers of the journey. Here, solar gravity reaches its full intensity, and velocities climb towards 600 kilometers per second or more. At these speeds, kinetic energy becomes so concentrated that the very act of moving through the increasingly dense solar atmosphere creates temperatures comparable to stellar interiors. But speed is only part of the destruction equation. The rate of acceleration itself creates tidal forces that would begin tearing 3I/ATLAS apart long before it reaches maximum velocity. Different parts of our visitor experience slightly different gravitational forces, with the side facing the Sun pulled more strongly than the trailing edge. These tidal forces increase as the square of proximity, becoming irresistible as 3I/ATLAS approaches the Sun. The atmosphere of the Sun provides the final element in this high-speed destruction story. As 3I/ATLAS encounters the increasingly dense solar atmosphere, atmospheric drag begins to compete with gravitational acceleration. The leading edge of our visitor encounters particles moving at high speeds relative to its trajectory, creating collision energies that instantly vaporize surface materials. This atmospheric interaction creates a feedback effect where vaporized material from 3I/ATLAS creates its own shockwave, compressing the solar atmosphere ahead of the remaining solid material. The energy released by this compression heats the surrounding plasma to temperatures exceeding those found in the Sun's core, creating a briefly localized region of extreme nuclear physics. The mathematics of destruction become clear. An object carrying the kinetic energy of nuclear weapons, moving at speeds that create fusion-level temperatures, encountering an environment already hot enough to sustain nuclear reactions continuously. The outcome is predetermined by physics operating on scales that make human technology appear insignificant. As 3I/ATLAS races toward its hypothetical solar encounter, humanity's network of space-based observatories would provide us with front-row seats to one of the most spectacular events in solar system astronomy. These robotic sentinels, positioned throughout our cosmic neighborhood, would capture every moment of the destruction in wavelengths invisible to human eyes, but rich with scientific information. The Solar Dynamics Observatory, stationed in geosynchronous orbit around Earth, represents our primary window into solar activity. Its instruments capture images of the Sun every 12 seconds across multiple wavelengths, creating a continuous movie of solar physics in action. For the 3I/ATLAS encounter, SDO would provide unprecedented documentation of how interstellar material interacts with stellar plasma. The Solar and Heliospheric Observatory, positioned at the gravitationally stable L, one point between Earth and the Sun, offers a different perspective with instruments designed specifically to study the solar corona. SOHO's coronagraphs can observe the Sun's outer atmosphere continuously, tracking objects as they approach and are destroyed by solar forces. Previous comet encounters have provided spectacular images through these instruments, but 3I/ATLAS would represent something entirely new. The Parker Solar Probe, humanity's closest approach to any star, would be uniquely positioned to observe the final moments of our interstellar visitor. Traveling within the Sun's outer corona, Parker's instruments could measure the direct effects of 3I/ATLAS's destruction on the local space environment, providing data impossible to obtain from any other vantage point. The detection timeline would unfold over several days as 3I/ATLAS approaches the Sun. Initially, our visitor would appear as nothing more than a moving point of light against the stellar background. But as solar heating intensifies, the characteristic signatures of cometary activity would emerge. A growing coma of gas and dust, brightening as volatile materials sublimate in the increasing solar radiation. Ground-based solar telescopes would contribute crucial observations during the approach phase. The Daniel K. Inouye Solar Telescope in Hawaii, with its 4-meter mirror, could potentially resolve details of the coma structure as 3I/ATLAS heats up. Radio telescopes would monitor for any electromagnetic emissions created by the interaction between the visitor's expanding gas cloud and solar magnetic fields. The spectroscopic data would prove invaluable for understanding 3I/ATLAS's composition. As different materials vaporize at different temperatures, the chemical fingerprints of an alien world would reveal themselves in the light of destruction. Instruments would detect elements and compounds that formed around another star, providing direct samples of interstellar chemistry delivered to our solar system. The final hours would bring increasingly dramatic observations as 3I/ATLAS encounters the Sun's corona. X-ray telescopes would record the intense radiation generated as solid matter transforms into million-degree plasma. The European Space Agency's solar orbiter, approaching the Sun from a different angle, would provide stereoscopic views of the destruction, allowing three-dimensional reconstruction of the event. The moment of maximum brightness would likely occur not when 3I/ATLAS reaches the Sun's surface, but during its passage through the corona, when kinetic energy converts most efficiently to radiation. This flash would briefly outshine many stellar phenomena, creating a beacon visible to solar observatories throughout the inner solar system. Radio emissions would tell their own story of destruction. As 3I/ATLAS's material becomes ionized in the solar environment, it would interact with magnetic field lines to produce radio waves at specific frequencies. These emissions would provide information about the strength and structure of solar magnetic fields in regions normally impossible to study directly. The aftermath observations would extend for weeks as dispersed material from 3I/ATLAS circulates through the solar atmosphere and solar wind. Particle detectors on spacecraft throughout the solar system might detect trace elements from our visitor, carried outward by solar processes to destinations as distant as the orbit of Saturn. This observational campaign would represent one of the most comprehensive studies of stellar object interaction ever conducted, providing data that would advance our understanding of both solar physics and interstellar chemistry for decades to come. The moment 3I/ATLAS crosses into the Sun's outermost corona marks the beginning of the end for our interstellar visitor. Here, at distances still greater than the radius of Earth's orbit around the Sun, the first wisps of million-degree plasma begin their assault on materials that have remained frozen since the dawn of another star system. The corona extends far beyond what most people imagine when they think of the Sun's atmosphere. This tenuous but incredibly hot region reaches temperatures of 2 to 5 million degrees Celsius, hundreds of times hotter than the Sun's visible surface. The physics behind this temperature inversion remains one of solar science's greatest mysteries. But for 3I/ATLAS, the mechanism matters less than the devastating effect. At first contact, our visitor encounters plasma densities roughly 1 billion times thinner than Earth's atmosphere at sea level. Yet what this environment lacks in density, it more than compensates for in temperature and energy. The corona contains charged particles moving at speeds that would be impossible in any earthly environment, accelerated by magnetic fields that twist and snap with explosive violence. The initial heating of 3I/ATLAS begins not with direct contact, but through radiation. The corona emits intense ultraviolet and X-ray radiation that begins breaking apart molecular bonds in the outer layers of our visitor's icy surface. Frozen water, carbon dioxide, and organic compounds that have maintained their chemical integrity for millions of years suddenly find themselves under assault by photons carrying energy levels that can shatter any molecular structure. Within minutes of coronal entry, the surface temperature of 3I/ATLAS climbs from its interstellar value of roughly minus 250 degrees Celsius to temperatures approaching the boiling point of water. This rapid heating creates enormous thermal stresses within the visitor's structure, as different materials expand at different rates, potentially causing the first fractures and fragmentations. The most volatile ices respond first to this thermal assault. Frozen carbon monoxide and nitrogen, components that may have formed in the cold outer regions of 3I/ATLAS's birth system, begin sublimating directly from solid to gas. This process creates the first visible signs of destruction as expanding gases form a thin atmosphere around our visitor, a pale echo of the magnificent comas that characterize comets during their normal solar encounters. But this is no ordinary comet encounter. The coronal environment immediately begins interacting with the newly formed gas cloud around 3I/ATLAS through processes unknown in the inner solar system. Solar wind particles, already accelerated to high speeds, collide with molecules escaping from our visitor's surface, creating collision cascades that generate characteristic radio emissions and high-energy particle radiation. The sun's magnetic field begins to take hold of ionized material, streaming from 3I/ATLAS, twisting and shaping the gas flows according to invisible lines of force that extend throughout the solar system. This magnetic interaction creates the first observable changes in the solar environment itself, subtle modifications to plasma flows that sensitive instruments can detect as our visitor's presence disturbs the normal patterns of coronal activity. As 3I/ATLAS continues its inward journey, the plasma density of its environment increases dramatically. What began as a tenuous interaction with sparse coronal material intensifies into a growing battle between the solid matter of another star system and the plasma physics of our sun. The outer layers of our visitor begin to stream away in an accelerating process of ablation, creating a tail of interstellar material that follows magnetic field lines back into space. The chemical signatures emerging from this first phase of destruction provide invaluable information about 3I/ATLAS's composition and origin. Spectroscopic analysis would reveal elements and isotopic ratios that formed under conditions very different from those found in our solar system, offering direct evidence of chemical processes operating around other stars billions of years ago. This initial encounter sets the stage for the increasingly violent interactions that await as our visitor continues its death spiral toward the nuclear furnace at the sun's heart. As 3I/ATLAS penetrates deeper into the solar atmosphere, it enters what solar physicists call the transition region, a boundary layer where the physics of destruction shift from gradual heating to catastrophic disintegration. Here, within roughly 2,000 kilometers of the sun's visible surface, temperatures plummet from the millions of degrees found in the corona to the mere thousands that characterize the solar photosphere below. This temperature gradient, paradoxical as it seems, creates the most violent environment our interstellar visitor has yet encountered. The transition region is where most of the sun's ultraviolet radiation originates, a band of the electromagnetic spectrum carrying enough energy to break apart not just molecular bonds, but atomic structures themselves. For 3I/ATLAS, this represents the point of no return, where solid matter begins its final transformation into ionized plasma. The heating rate accelerates exponentially as our visitor descends through this zone. Surface temperatures climb from hundreds of degrees to thousands of degrees within minutes, causing different materials to vaporize in a sequence determined by their physical properties. Water ice, the most abundant component of 3I/ATLAS, reaches its sublimation point first, transforming directly from solid to vapor in vast clouds that expand rapidly in the low-pressure solar environment. This expansion is not gentle. As ice sublimates, it can increase in volume by factors of thousands, creating explosive outgassing that fragments the remaining solid structure of our visitor. Imagine a mountain-sized block of ice suddenly deciding to become gas. The forces involved are sufficient to shatter the strongest materials known to science. Carbon dioxide follows water in the sublimation sequence, adding its own explosive contribution to the growing chaos. 3. I/ATLAS, likely contains significant amounts of frozen carbon dioxide based on observations of its real-world behavior, and this component vaporizes with particular violence. The rapid phase change creates shock waves that propagate through the remaining solid material, fracturing and weakening any coherent structure. The most refractory materials, rocky components and organic compounds that formed at higher temperatures in the original protoplanetary disk, resist the initial heating, but cannot withstand the intensifying radiation environment. Silicon-based minerals begin breaking down into their component elements, while complex organic molecules decompose into simpler carbon and hydrogen compounds. As each layer of 3I/ATLAS vaporizes, it reveals material from deeper within the object's structure. This process creates a kind of geological excavation in reverse, exposing the interior composition of our interstellar visitor to direct solar radiation. Different layers may have formed under different conditions in the original star system, creating a stratified record of planetary formation processes, now being unveiled by stellar heat. The electromagnetic spectrum tells the story of this destruction in exquisite detail. Each element and compound produces characteristic emission lines when heated to incandescence, creating a spectroscopic fingerprint that reveals not just the composition of 3I/ATLAS, but the physical conditions under which its materials originally formed. Instruments throughout the solar system would record these signatures, building a comprehensive chemical analysis of matter from another star. The material streaming away from 3I/ATLAS doesn't simply disappear. It becomes part of the solar wind, carried throughout the solar system by magnetic field lines and plasma flows. For a brief period, our entire solar system would contain trace amounts of matter that originated around another star, distributed by solar processes to destinations as distant as the outer planets. The mechanical destruction accompanying this chemical breakdown is equally dramatic. As different materials vaporize at different rates, thermal stresses create fracture patterns that split 3I/ATLAS into ever smaller fragments. Each fragment becomes its own center of sublimation and heating, multiplying the surface area exposed to solar radiation and accelerating the overall destruction process. By the time our visitor reaches the lower boundary of the transition region, little remains of its original solid structure. What began as a coherent object several kilometers across has become a diffuse cloud of gas, plasma, and microscopic debris, all heated to temperatures that would be lethal to any conceivable form of life. In the final kilometers of its journey, what remains of 3I/ATLAS faces a cosmic tug-of-war between two irresistible forces: the sun's gravity pulling the debris inward toward ultimate destruction, and the solar wind pushing the vaporized material outward into space. This battle between opposing forces creates some of the most spectacular and scientifically valuable phenomena in our hypothetical encounter. The solar wind at this depth in the sun's atmosphere carries enormous energy and momentum. Charged particles accelerated to speeds exceeding 400 kilometers per second create a plasma environment more violent than anything found elsewhere in our solar system. These particles don't simply flow past the remains of 3I/ATLAS. They interact directly with the ionized material through electromagnetic processes that can accelerate debris to even higher velocities. As gravity continues pulling the densest fragments of our visitor toward the solar surface, the expanding cloud of vaporized material begins moving against this inward flow. The lighter elements, hydrogen and helium, created by the breakdown of water and organic compounds, are caught up in the solar wind and accelerated outward at tremendous speeds. Heavier elements, silicon, iron, and carbon, resist this outward acceleration, but cannot overcome the gravitational pull, drawing them deeper into the solar atmosphere. This separation process creates a kind of cosmic distillation where different elements follow different trajectories based on their atomic masses and ionization states. The result is a complex three-dimensional structure of flowing plasma that would be visible to instruments as a distinctive disruption in the normal patterns of solar wind and magnetic field lines. The electromagnetic interactions become increasingly violent as the plasma density rises. Magnetic field lines, normally invisible and intangible, become loaded with charged particles from 3I/ATLAS and begin to glow with characteristic emission lines. These magnetic structures can suddenly snap and reconnect, releasing energy equivalent to nuclear explosions and accelerating particles to near-relativistic speeds. The remaining solid debris of our visitor experiences forces that dwarf anything encountered during its million-year interstellar journey. Tidal forces from solar gravity attempt to stretch and deform any coherent structures, while radiation pressure from the intense solar energy output pushes against exposed surfaces. The combination creates stress levels that would pulverize the strongest materials known to science. In this environment, the boundary between matter and energy begins to blur. Kinetic energy from the high-speed motion of 3I/ATLAS converts directly to thermal energy through collision processes, heating the surrounding plasma to temperatures that can sustain nuclear fusion reactions. For brief moments, the destruction of our interstellar visitor creates conditions similar to those found in the Sun's core, where hydrogen nuclei overcome their natural repulsion and fuse into helium. The spectacle would be visible throughout the inner solar system as a temporary brightening of the Sun's corona. The energy released by the complete vaporization of 3I/ATLAS, while insignificant compared to the Sun's total output, would create localized regions of enhanced brightness lasting for hours or days. These bright zones would appear as temporary active regions, similar to solar flares but triggered by the introduction of foreign material rather than magnetic instabilities. The timing of material ejection creates observable phenomena that would persist long after the destruction of 3I/ATLAS itself. Different elements ejected at different times would arrive at Earth's orbit weeks or months apart, creating a temporal record of the destruction process that could be detected by particle instruments throughout the solar system. Some material might achieve escape velocity, joining the interstellar medium as high-speed ejecta, carrying the chemical signatures of both 3I/ATLAS's original composition and the nuclear processes that occurred during its destruction. These particles would begin their own million-year journeys through the galaxy, potentially carrying evidence of stellar encounters to distant star systems. The final moments of this cosmic race determine whether any trace of 3I/ATLAS survives to reach the Sun's photosphere, or whether the solar wind succeeds in dispersing all remaining material back into space before the ultimate encounter with stellar fire. As the remains of 3I/ATLAS descend into the deepest layers of the solar atmosphere, they enter a realm where the familiar rules of chemistry surrender to the exotic physics of stellar interiors. Here, at temperatures exceeding 10,000 degrees Celsius and pressures millions of times greater than Earth's atmosphere, matter exists in states unknown in terrestrial laboratories, and the very atoms that once comprised our interstellar visitor undergo transformations that would be impossible anywhere else in the solar system. The unique chemistry that 3I/ATLAS carried from its distant birth system becomes a scientific treasure during these final moments of destruction. The real 3I/ATLAS showed unusual concentrations of carbon dioxide relative to water, a signature that suggested formation under conditions very different from those that created our solar system's comets. In our hypothetical encounter, this exotic chemistry provides invaluable information about planetary formation processes around other stars. Water molecules, the most abundant component of most comets, decompose rapidly at these temperatures. The familiar H2O splits into its constituent hydrogen and oxygen atoms, but the story doesn't end there. The free hydrogen, being the lightest element, attempts to escape upward through the solar atmosphere, while oxygen atoms tend to combine with other elements or exist as isolated ions in the plasma environment. The carbon dioxide that makes 3I/ATLAS chemically distinctive follows a more complex path. At temperatures exceeding several thousand degrees, CO2 molecules dissociate into carbon and oxygen atoms, but the high-energy environment allows for chemical reactions impossible under normal conditions. Carbon atoms can combine with hydrogen to form methane or other hydrocarbons, or with oxygen to create carbon monoxide in ratios determined by the local temperature and pressure conditions. Perhaps most remarkably, the extreme environment begins breaking down atomic nuclei themselves. At temperatures approaching 100,000 degrees, the kinetic energy of atomic collisions becomes sufficient to strip electrons completely from their nuclei, creating a fully ionized plasma where atoms exist only as bare nuclei surrounded by a sea of free electrons. The spectroscopic signatures created by this atomic destruction tell the story of 3I/ATLAS's origin in unprecedented detail. Each element emits light at characteristic wavelengths when heated to incandescence, but the extreme conditions near the solar surface create emission lines that reveal isotopic ratios, nuclear structure, and even details about the stellar environment where these atoms originally formed. Trace elements within 3I/ATLAS provide the most valuable scientific information. Elements like deuterium, carbon-13, and nitrogen-15 exist in ratios that depend on the nuclear physics operating in the host star and the chemical evolution of its protoplanetary disk. The destruction of our visitor creates a brief opportunity to measure these ratios with precision impossible to achieve through telescopic observations of distant star systems. The magnetic environment adds another layer of complexity to the chemical processes. Charged particles created by the ionization of 3I/ATLAS material follow helical paths along magnetic field lines, creating distinctive patterns of emission and absorption that encode information about both the material composition and the local magnetic field structure. As temperatures rise beyond 100,000 degrees in the final moments before reaching the photosphere, even more exotic processes become possible. Nuclear reactions that normally require the extreme conditions found in stellar cores can occur briefly in the superheated plasma created by our visitor's destruction. Fusion reactions between hydrogen nuclei create helium and release energy, while spallation reactions break apart heavier nuclei into lighter elements. These nuclear processes create isotopic signatures that would be detectable throughout the solar system for months after the event. Spacecraft equipped with particle detectors could identify atoms that originated in 3I/ATLAS by their unusual isotopic ratios, tracking the distribution of interstellar material as it disperses through solar wind and magnetic field processes. The chemistry of destruction also reveals information about the age and history of our visitor. Cosmic ray exposure during its million-year journey would have created distinctive isotopic modifications that survive even the extreme heating of solar encounter. These signatures provide direct measurements of how long 3I/ATLAS traveled through interstellar space and the radiation environment it encountered during that journey. In the final analysis, the chemistry in HEL provides a unique laboratory for studying matter under conditions impossible to replicate anywhere else, while simultaneously revealing the deepest secrets of planetary formation around distant stars. As 3I/ATLAS completes its transformation from solid matter to ionized plasma, it leaves behind a glowing trail that would rank among the most spectacular phenomena ever observed in solar physics. This plasma trail, stretching across thousands of kilometers of the solar atmosphere, becomes a temporary but brilliant scar that tells the story of an interstellar visitor's ultimate sacrifice to stellar forces. The trail forms as ionized material from our visitor follows the sun's magnetic field lines, creating luminous structures that persist long after the original solid matter has been completely vaporized. These magnetic field lines act like invisible highways for charged particles, guiding the plasma along curved paths that loop and twist through the solar atmosphere according to the complex geometry of solar magnetism. The brightness of this trail would far exceed anything produced by normal solar activity. While solar flares and coronal mass ejections can create temporary brightenings in specific regions, the complete vaporization of several cubic kilometers of solid matter creates light emissions spread across multiple layers of the solar atmosphere simultaneously. Ground-based solar telescopes would record this event as one of the brightest transient phenomena ever observed on the Sun. Different elements contribute different colors to this cosmic fireworks display. Hydrogen, the most abundant element in 3I/ATLAS's composition, glows with the characteristic red light of hydrogen alpha emission. Oxygen produces green and red emissions, while carbon creates distinctive blue-green hues. The overall effect would be a rainbow of stellar fire, with colors determined by the original chemical composition of our interstellar visitor. The three-dimensional structure of the plasma trail reveals information about solar magnetic field geometry that would be impossible to obtain through any other means. As charged particles from 3I/ATLAS follow magnetic field lines, they trace out the invisible architecture of solar magnetism, creating a kind of magnetic field visualization on a stellar scale. The duration of the trail's visibility depends on the complex interplay between magnetic confinement and plasma dispersion processes. Some elements might remain trapped along magnetic field lines for hours or days, creating persistent bright regions in the solar atmosphere. Others might escape quickly into the solar wind, carrying their light emissions outward through the solar system. The spectroscopic information contained in the plasma trail provides an unprecedented opportunity to study the isotopic composition of interstellar material. As different isotopes of the same element emit light at slightly different wavelengths, high-resolution spectroscopy could reveal details about nuclear processes that occurred in 3I/ATLAS's birth system billions of years ago. The interaction between the plasma trail and existing solar activity creates additional layers of complexity and scientific value. If the 3I/ATLAS encounter occurred during a period of high solar activity, the introduction of foreign plasma could trigger enhanced flare activity or modify the structure of existing active regions. These interactions would provide insights into solar plasma physics that would be impossible to obtain through theoretical modeling alone. Radio emissions from the plasma trail would be detectable by radio telescopes throughout the inner solar system. As charged particles spiral along magnetic field lines, they produce synchrotron radiation at frequencies determined by the local magnetic field strength and particle energies. These radio signals would carry information about both the composition of 3I/ATLAS and the magnetic environment it encountered during destruction. The trail's evolution over time creates a kind of cosmic time-lapse photography, showing how stellar magnetic fields transport and disperse material through the solar atmosphere. Particle tracking through this evolution would reveal circulation patterns and magnetic field dynamics, operating on scales impossible to study through conventional solar observations. Some material from the plasma trail would eventually escape the solar atmosphere entirely, joining the solar wind as high-energy particles carrying the chemical signatures of another star system. These particles would propagate throughout the solar system, potentially reaching the orbits of outer planets and creating detectable signals in particle detectors aboard spacecraft throughout our cosmic neighborhood. The plasma trail represents the final visible legacy of 3I/ATLAS's hypothetical solar encounter, a luminous monument to the power of stellar forces and the scientific value of cosmic catastrophe. The question that naturally arises from our journey through the solar atmosphere is whether any remnant of 3I/ATLAS could actually reach the Sun's surface, the photosphere that defines the visible edge of our star. The answer reveals fundamental truths about stellar physics and the overwhelming dominance of radiation pressure over gravitational attraction in the deepest layers of stellar atmospheres. To understand why reaching the solar surface is virtually impossible, we must appreciate the energy densities involved in the final stages of our hypothetical encounter. At depths approaching the photosphere, the energy flux from solar radiation becomes so intense that it exerts physical pressure on any material attempting to descend further. This radiation pressure can exceed the gravitational force pulling material inward, creating an effective barrier that prevents most infalling matter from reaching the stellar surface. The photosphere itself represents a boundary layer where the sun transitions from being transparent to opaque. Below this level, the plasma density becomes so high that photons cannot escape directly into space, instead scattering repeatedly through the dense material before eventually reaching the surface. The energy trapped by this scattering process creates pressures and temperatures that would instantly vaporize and disperse any remaining solid or liquid material. Even if fragments of 3I/ATLAS somehow survived the journey through the corona and transition region, they would encounter conditions at the photosphere that make survival impossible. Temperatures exceed 5,500 degrees Celsius, hot enough to vaporize any known material, while the pressure reaches levels comparable to those found deep within planetary atmospheres. The physics of radiation pressure provides the final barrier to surface impact. Each photon carries momentum, and when billions upon billions of photons per second encounter ascending plasma from vaporized cometary material, they collectively exert a force that can overcome gravity. This is the same process that creates the spectacular tails of bright comets, but operating at intensity levels millions of times greater. Historical observations of sun-grazing comets support this theoretical understanding. Even the largest and most cohesive comets begin disintegrating while still millions of kilometers from the solar surface. Comet Ison, which briefly captured global attention during its 2013 encounter, was completely destroyed while still farther from the Sun than Mercury's orbit. Smaller fragments might survive closer approaches, but none have ever been observed to reach the photosphere intact. The fate of individual atoms tells a more subtle story. While no macroscopic object can reach the solar surface, the atomic components of 3I/ATLAS would eventually become incorporated into the Sun's outer layers. These atoms would join the convective circulation patterns that transport material between the photosphere and the interior, potentially carrying chemical signatures from our interstellar visitor throughout the outer portions of our star. The mixing timescales for this process operate on geological timeframes. Material deposited in the Sun's outer atmosphere takes thousands of years to circulate through convective cells and become homogeneously distributed. This means that trace chemical signatures from 3I/ATLAS might remain detectable in solar spectra for millennia after the encounter, creating a permanent record of our visitor's contribution to solar chemistry. The energy balance equation reveals why stellar surfaces remain essentially inviolate to external bombardment. The Sun radiates roughly 3.8 times 10 to the 26th watts continuously, representing the conversion of 4 million tons of matter into energy every second through nuclear fusion. Against this overwhelming energy output, even the most massive comet or asteroid represents an insignificant perturbation. The concept of the Roche limit provides another perspective on why objects cannot survive close approaches to massive bodies. Just as Jupiter's tidal forces prevent moons from forming too close to the giant planet, the Sun's gravitational gradient creates stress levels that exceed the structural strength of any conceivable material long before the object could reach the stellar surface. The impossibility of deep impact paradoxically increases the scientific value of our hypothetical encounter. Since 3I/ATLAS cannot actually collide with the Sun, all of its material becomes available for spectroscopic analysis during the destruction process. This creates a more complete chemical inventory than would be possible if fragments survived to impact the surface and disappear from observation. Understanding these physical limits helps us appreciate why the Sun has remained essentially unchanged, despite billions of years of bombardment by comets, asteroids, and interstellar objects throughout its history. One of the most counterintuitive aspects of our hypothetical encounter is how little effect 3I/ATLAS would have on the Sun itself. Despite the spectacular destruction we've witnessed and the enormous energies involved in vaporizing several cubic kilometers of interstellar ice, our star would barely notice this cosmic intrusion. Understanding this disparity reveals the true scales of stellar physics and helps us appreciate just how dominant stars are within their gravitational domains. To put the energy scales in perspective, consider that 3I/ATLAS, with its estimated mass of trillions of kilograms, represents roughly 1/10 billionth of the mass that the Sun converts to energy every single day through nuclear fusion. The complete conversion of our visitor's mass to energy, while spectacular from our perspective, would power the Sun for perhaps a few microseconds at most. The Sun's energy output operates on scales that dwarf terrestrial experience. Every second, nuclear reactions in the solar core release energy equivalent to detonating 100 billion hydrogen bombs simultaneously. This process has continued steadily for over 4.5 billion years and will continue for approximately 5 billion more. Against this continuous nuclear inferno, the kinetic energy of an infalling comet becomes essentially negligible. Even the mechanical effects of 3I/ATLAS's destruction would be minimal in solar terms. The plasma disturbances created by our visitor's vaporization might create temporary ripples in the solar atmosphere, similar to dropping a pebble into an ocean. These disturbances would propagate outward through the corona at the speed of sound in the solar plasma, creating temporary pressure waves that would dissipate within hours or days. The magnetic field interactions tell a more complex story. While 3I/ATLAS cannot mechanically damage the Sun, the introduction of ionized material into the solar magnetic environment could trigger enhanced activity in ways that might be observable from Earth. Solar flares and coronal mass ejections often result from magnetic field instabilities, and the additional plasma from our visitor could potentially catalyze such events. However, even these enhanced magnetic phenomena would represent normal solar variability rather than fundamental changes to stellar behavior. The Sun routinely experiences magnetic reconnection events that release energies far exceeding anything that 3I/ATLAS could contribute. Our visitor's main effect would be to provide additional material for these natural processes rather than to create entirely new categories of solar activity. The chemical impact offers a different perspective on solar response. While 3I/ATLAS cannot change the Sun's energy output or magnetic behavior significantly, it would contribute trace elements to the solar atmosphere that might remain detectable for extended periods. The unusual carbon dioxide composition that characterizes the real 3I/ATLAS would create subtle changes in solar spectral lines that sensitive instruments could potentially observe. These chemical signatures would be overwhelmed by the Sun's existing composition within relatively short timeframes, as convective mixing distributes the foreign material throughout the outer layers of our star. The timescales involved range from months for surface mixing to millennia for complete homogenization. But even during the period of maximum detectability, the chemical changes would represent tiny perturbations to existing solar composition. The radiative response provides perhaps the most observable consequence of our hypothetical encounter. The energy released by 3I/ATLAS's destruction would create temporary brightening in specific wavelengths corresponding to the excited atoms and ions created during the vaporization process. This brightening would be detectable by solar observatories as a transient event lasting hours to days, but it would not affect the Sun's overall luminosity in any measurable way. Solar monitoring satellites would record this event as an interesting anomaly rather than a significant change to solar behavior. The enhanced emissions would appear in their data as temporary spikes in specific spectral lines, providing valuable scientific information while confirming that the Sun's fundamental processes remain unaffected. The long-term solar response would be essentially zero. Within years of the encounter, any trace of 3I/ATLAS's contribution to solar chemistry would become undetectable, mixed into the vast reservoir of stellar material by convective processes. The Sun would continue its steady hydrogen-burning existence as if the encounter had never occurred, maintaining the stable energy output that has sustained life on Earth for billions of years. This immunity to external perturbations helps explain how stars can maintain steady nuclear burning for such extended periods, despite the cosmic bombardment they must experience throughout their lifetimes. while the Sun itself would remain essentially unaffected by our hypothetical encounter with 3I/ATLAS. The destruction of our interstellar visitor would create ripple effects throughout the solar system that could be detected by sensitive instruments for months or even years after the event. These cosmic echoes would provide a unique opportunity to study how stellar processes distribute material and energy across interplanetary space. The most immediate effect would be the enhancement of the solar wind, carrying trace elements from 3I/ATLAS to every corner of our cosmic neighborhood. The solar wind typically consists of hydrogen and helium ions, streaming outward at speeds exceeding 400 kilometers per second. But the destruction of our visitor would temporarily enrich this flow with heavier elements and isotopic signatures characteristic of interstellar material. Spacecraft throughout the solar system equipped with particle detectors would begin registering these enhanced levels within days or weeks of the encounter, depending on their distance from the Sun. The timing of detection would itself provide valuable information about solar wind propagation speeds and the three-dimensional structure of magnetic field lines that guide charged particles through interplanetary space. The isotopic signatures carried by these particles would be unmistakable fingerprints of their origin. Elements created in the nuclear environment of 3I/ATLAS's birth system would carry isotopic ratios different from those found in solar system material, allowing scientists to track the distribution of interstellar matter throughout our cosmic neighborhood with unprecedented precision. Earth's magnetosphere would provide a natural laboratory for studying these effects. As enhanced solar wind particles interact with our planet's magnetic field, they would create subtle modifications to the radiation belt surrounding Earth. Satellites monitoring space weather would detect changes in particle flux and energy distributions that encode information about the composition and timing of 3I/ATLAS's destruction. The aurora phenomenon offers another window into these solar system-wide effects. Enhanced solar wind activity typically creates more frequent and intense auroral displays as charged particles interact with Earth's upper atmosphere. The unique chemical composition of particles originating from 3I/ATLAS might create auroral colors or spectral features not normally observed, providing ground-based observers with direct evidence of interstellar material reaching Earth's vicinity. Mars presents a particularly interesting case for studying these effects. Without a strong magnetic field to deflect solar wind particles, the red planet's atmosphere interacts directly with enhanced solar wind flow. Spacecraft in Mars orbit would detect changes in atmospheric chemistry as particles from 3I/ATLAS contribute to the ongoing atmospheric escape processes that have been shaping Mars for billions of years. The outer solar system offers yet another perspective on these propagating effects. Jupiter's massive magnetosphere acts like a cosmic particle accelerator, trapping charged particles and accelerating them to enormous energies. Enhanced solar wind from the 3I/ATLAS encounter would eventually reach Jupiter's system, contributing to radiation belt processes and potentially affecting the space environment around the gas giant's moons. Gas giant magnetospheres also serve as natural laboratories for studying particle physics under conditions impossible to replicate on Earth. The injection of interstellar material with unique isotopic signatures would provide traceable markers for studying magnetic field topology, particle acceleration mechanisms, and the long-term evolution of planetary radiation environments. Comet and asteroid populations throughout the solar system would provide another record of the encounter's effects. These small bodies, with their weak gravitational fields, could capture particles from the enhanced solar wind and preserve them in their surface materials for millions of years. Future sample return missions might detect trace signatures of 3I/ATLAS embedded in the regoliths of objects throughout the solar system. The interplanetary dust environment would also be affected by our hypothetical encounter. The vaporization of 3I/ATLAS would create microscopic debris that disperses through the solar system at high velocities, contributing to the existing population of interplanetary dust particles that spacecraft encounter during their journeys through space. Long-term climate effects on Earth would be minimal, but potentially detectable by sensitive instruments. The temporary enhancement of certain elements in Earth's upper atmosphere might create subtle changes in atmospheric chemistry that persist for years after the initial event, providing atmospheric scientists with natural traces for studying upper atmospheric dynamics and chemistry. These solar system-wide echoes would represent the lasting legacy of our interstellar visitors' encounter with solar fire, distributing samples of alien chemistry throughout our cosmic neighborhood and creating research opportunities that would advance multiple fields of space science simultaneously. The complete destruction of 3I/ATLAS in our hypothetical solar encounter would create one of the most scientifically valuable events in the history of astronomy, providing unprecedented insights into stellar physics, interstellar chemistry, and the fundamental processes governing matter under extreme conditions. The scientific return from such an event would advance our understanding across multiple disciplines simultaneously. Solar physics would benefit enormously from observing how foreign material interacts with the complex environment of stellar atmospheres. Currently, our knowledge of solar atmospheric structure comes primarily from theoretical models and indirect observations. The introduction of traceable material from 3I/ATLAS would provide direct measurements of temperature, density, and magnetic field strength at various depths within the solar atmosphere, essentially using our visitor as a probe to map regions impossible to study through conventional means. The spectroscopic data alone would represent a revolution in our understanding of stellar spectroscopy. As different elements from 3I/ATLAS vaporize and emit characteristic radiation, astronomers would obtain precise measurements of atomic and molecular behavior under conditions that exceed anything achievable in terrestrial laboratories. These measurements would improve our ability to interpret the spectra of distant stars and provide calibration data for stellar atmosphere models used throughout astronomy. Interstellar chemistry would emerge as perhaps the greatest beneficiary of this cosmic experiment. 3I/ATLAS represents a direct sample of material that formed around another star, preserved in the cosmic deep freeze for millions of years. The destruction process would reveal not just the elemental composition of this alien matter, but also its isotopic ratios, molecular structures, and the physical conditions that prevailed during its formation. The isotopic signatures would be particularly valuable, providing direct evidence of nuclear processes operating in other stellar systems. Different stars produce different isotopic ratios of elements through varying fusion processes, and these signatures remain embedded in planetary material formed from stellar debris. By analyzing the isotopes released during 3I/ATLAS's destruction, scientists could infer the mass, age, and nuclear burning history of the star that created this material billions of years ago. Plasma physics would gain invaluable data about matter behavior under extreme conditions. The transformation of solid ice into million-degree plasma occurs through processes that we can model theoretically, but rarely observe directly. The 3I/ATLAS encounter would provide real-time observations of these phase transitions, offering insights applicable to fusion reactor design and laboratory plasma physics. The magnetic field interactions would advance our understanding of stellar magnetism and its role in energy transport throughout stellar atmospheres. As ionized material from 3I/ATLAS follows magnetic field lines and creates observable disturbances in plasma flow, scientists would obtain three-dimensional maps of solar magnetic field structure with resolution impossible to achieve through other observational techniques. Astrobiology would also benefit from studying the organic compounds likely present in 3I/ATLAS. While these complex molecules would be destroyed during the solar encounter, the breakdown products and their spectroscopic signatures would reveal information about organic chemistry operating under the conditions found in other stellar systems. This data would inform models of how organic compounds form and evolve in different planetary environments throughout the galaxy. Planetary formation theory would receive crucial calibration data from the destruction of our interstellar visitor. The physical and chemical properties revealed during the encounter would provide direct measurements of conditions in alien protoplanetary disks, testing theoretical models that currently rely on observations of distant star-forming regions and computer simulations. The particle acceleration processes observed during 3I/ATLAS's destruction would contribute to high-energy astrophysics research. The mechanisms that accelerate atoms and ions to high speeds during stellar encounters operate throughout the universe in environments ranging from stellar corona to supernova remnants. Understanding these processes in detail would improve our interpretation of high-energy phenomena observed around other stars and in other galaxies. Nuclear physics would gain from observing fusion and spallation reactions occurring under natural conditions that exceed anything achievable in particle accelerators. The extreme environment created during 3I/ATLAS's final moments would briefly recreate conditions similar to those found in stellar cores, providing natural laboratories for studying nuclear processes under conditions impossible to replicate on Earth. The interdisciplinary nature of this scientific bonanza would create synergies between fields that rarely interact directly. Solar physicists working with nuclear physicists, spectroscopists collaborating with planetary scientists, and plasma physicists sharing data with astrobiologists would accelerate scientific progress across multiple disciplines simultaneously. Perhaps most importantly, the event would demonstrate the scientific value of studying extreme scenarios and rare events, encouraging investment in observational capabilities and theoretical frameworks needed to understand the most energetic phenomena in our universe. The vaporization of 3I/ATLAS would create a unique opportunity to analyze the chemical composition of matter that formed around another star, providing direct evidence of planetary formation processes operating under conditions very different from those that created our solar system. This alien chemistry, preserved in ice for millions of years during the journey through interstellar space, would reveal secrets about stellar evolution and planetary development that we could never obtain through telescopic observations alone. The isotopic ratios embedded within 3I/ATLAS's composition would tell the story of nuclear processes operating in its birth system billions of years ago. Different types of stars produce characteristic isotopic signatures through their fusion reactions, and these fingerprints remain embedded in any planetary material that forms from stellar debris. By measuring the precise ratios of carbon-12 to carbon-13, nitrogen-14 to nitrogen-15, and oxygen-16 to oxygen-18, scientists could infer fundamental properties of the star system where our visitor originated. The deuterium content would be particularly revealing, as this heavy isotope of hydrogen provides information about both stellar nucleosynthesis and the chemical evolution of the galaxy. Deuterium abundance varies depending on when and where in the galaxy's history planetary material formed, creating a kind of cosmic clock that reveals the age and galactic location of 3I/ATLAS's birth system. The organic compounds within our interstellar visitor would provide unprecedented insights into carbon chemistry operating under alien conditions, while these complex molecules would be destroyed during the solar encounter. The breakdown products would reveal information about the original molecular structures and the chemical processes that created them. The presence of amino acids, carbohydrates, or other biologically relevant compounds would have profound implications for astrobiology and our understanding of how life's building blocks form throughout the galaxy. The mineral composition would reveal the rocky component of 3I/ATLAS's birth system, providing direct samples of alien geology. Different stellar environments produce different ratios of rock-forming elements, and these signatures remain preserved in solid particles embedded within cometary ice. Silicon to magnesium ratios, iron content, and the presence of rare earth elements would all provide clues about the metallicity and chemical evolution of the original protoplanetary disk. The water chemistry itself would carry valuable information about the temperature and radiation environment where three I/A-TLAS formed. Water molecules can incorporate deuterium at different rates depending on local conditions, creating isotopic signatures that reveal whether ice formation occurred in the cold outer regions of a protoplanetary disk or in warmer zones closer to the central star. The carbon dioxide that makes the real 3I/A-TLAS chemically distinctive would provide its own treasure trove of information about alien atmospheric and surface processes. The isotopic composition of both carbon and oxygen within CO2 molecules reveals information about the oxidation state and chemical evolution of the environment where these compounds originally formed. Noble gases trapped within the ice matrix would provide additional chemical archaeology. Helium, neon, and argon isotopes created by cosmic ray interactions during the interstellar journey would reveal information about the radiation environment our visitor encountered during its million-year voyage. These measurements would help scientists understand the physics of interstellar space and the processes that modify small bodies during their journeys between star systems. The destruction process itself would create new chemical signatures as alien matter interacts with the solar environment. Nuclear reactions triggered by the extreme conditions near the Sun would produce isotopes that don't exist naturally in solar system material, creating artificial traces that scientists could follow through the solar system for years after the encounter. The sulfur chemistry would reveal information about volcanic or hydrothermal processes that might have operated in three I/A-TLAS's birth system. Sulfur compounds carry distinctive isotopic signatures that depend on the redox conditions and temperature environments where they formed, potentially revealing whether the original system contained planets with active geological processes. Metal abundances would provide information about the nucleosynthesis history of our visitor's stellar neighborhood. Elements heavier than iron are created primarily in supernova explosions, and their relative abundances reflect the stellar evolution history of the galactic region where 3I/ATLAS originated. The chemical gradients within different layers of our visitor would reveal information about the structure and evolution of its birth system's protoplanetary disk. Material that formed at different distances from the central star would carry different chemical signatures, creating a stratified record of alien planetary formation processes preserved within our interstellar visitor. Perhaps most remarkably, the complete chemical inventory would allow scientists to reconstruct the physical and chemical conditions that prevailed in another stellar system billions of years ago, essentially using 3I/ATLAS as a time capsule containing direct evidence of planetary formation processes operating throughout the galaxy. Our hypothetical encounter between 3I/ATLAS and the Sun gains perspective when compared to actual solar impacts that astronomers have observed throughout the space age. These real-world events provide both validation for our theoretical understanding and context for appreciating what makes our interstellar visitors encounter unique among cosmic collisions. Comet ISON's 2013 encounter with the Sun represents perhaps the most intensively studied example of a sun-grazing comet's destruction. This visitor, originally estimated at roughly 1 kilometer in diameter, began showing signs of fragmentation while still several million kilometers from the solar surface. Ground-based and space-based observatories worldwide documented its progressive disintegration, revealing how solar radiation and tidal forces systematically demolish infalling objects long before they can reach the stellar surface. The Kreutz-group comets provide an even more dramatic comparison. These fragments of a larger comet that broke apart centuries ago regularly plunge toward the Sun, with the Solar and Heliospheric Observatory discovering several thousand such objects since the 1990s. Most of these sun grazers are completely vaporized during their encounters, disappearing entirely from observational records as they're absorbed into the solar atmosphere. Comet Lovejoy's remarkable 2011 survival of its solar encounter demonstrated the extreme end of what's possible for cometary material approaching the Sun. This comet dove to within 140,000 kilometers of the solar surface yet emerged with a surviving nucleus, though dramatically reduced in size and altered in composition. The fact that Lovejoy's survival was considered extraordinary highlights just how lethal the solar environment is to infalling objects. What makes 3I/ATLAS unique in this context is its interstellar origin and the chemical signatures this journey has created. While sun-grazing comets from our own solar system provide spectacular displays of destruction, they don't carry the scientific treasure trove of alien chemistry that our hypothetical visitor would deliver to the solar furnace. The size difference between 3I/ATLAS and most observed sun-grazers would create a qualitatively different type of event. While typical Kreutz group fragments measure tens to hundreds of meters across, our interstellar visitor stretches several kilometers in its longest dimension. This size difference means that 3I/ATLAS would produce destruction effects lasting much longer and creating more dramatic disturbances in the solar atmosphere. The velocity differences tell another important part of the comparison story. Solar system comets approaching the Sun typically reach speeds of 200 to 300 kilometers per second during their perihelion passages. 3I/ATLAS, coming from interstellar space with its own hyperbolic excess velocity, would be moving significantly faster, creating more intense heating and more violent destruction processes. The composition differences provide perhaps the most scientifically valuable contrast. Solar system comets formed from the same nebular material that created our planets, carrying chemical signatures that reflect local conditions 4.6 billion years ago. 3I/ATLAS represents material from an entirely different stellar environment, potentially with different elemental abundances, isotopic ratios, and organic chemistry reflecting processes that operated around another star. Historical impacts provide additional context for understanding the significance of our hypothetical encounter. The collision of comet Shoemaker-Levy 9 with Jupiter in 1994 demonstrated the explosive energies released when solar system objects collide with massive bodies. While that event involved impact with a planetary atmosphere rather than stellar material, it showed how such collisions create temporary disturbances that can be observed across the solar system. The frequency of solar impacts offers another perspective on our scenario's significance. The Sun encounters small debris regularly, with tiny particles burning up in the solar atmosphere constantly. However, objects the size of 3I/ATLAS encounter the Sun perhaps once every few centuries, making our hypothetical event extraordinarily rare from a human perspective, while being relatively routine on cosmic timescales. The observational technology available for studying our hypothetical encounter far exceeds anything available during previous solar impacts. Modern solar observatories like the Parker Solar Probe and Solar Orbiter provide unprecedented close-up views of solar processes, while ground-based facilities like the Daniel K. Inouye Solar Telescope offer resolution capabilities that would capture details impossible to observe during earlier events. The scientific return from 3I/ATLAS would dwarf that obtained from previous solar encounters, due to both the improved observational capabilities and the unique interstellar chemistry that our visitor would bring to its destruction. While previous events advanced our understanding of solar physics and cometary science, the alien nature of 3I/ATLAS's composition would create research opportunities extending across multiple scientific disciplines. The comparison ultimately highlights how our hypothetical encounter represents a perfect storm of scientific opportunity. A large interstellar object carrying alien chemistry, observed with modern instrumentation, and destroyed in the ultimate laboratory of stellar physics. The destruction of 3I/ATLAS in our hypothetical solar encounter would create disturbances in the solar atmosphere that could affect technological systems throughout the inner solar system, though these effects would be modest compared to the natural variations in solar activity that our civilization already monitors and prepares for on a daily basis. Understanding these potential impacts provides insight into the interconnected nature of solar-terrestrial relationships and the sophisticated infrastructure we've developed to monitor space weather. The initial plasma disturbances created by our visitors' vaporization would propagate outward through the solar corona at speeds approaching 1,000 kilometers per second, creating pressure waves similar to those produced by solar flares, but with distinctive characteristics reflecting the foreign composition of the source material. These disturbances would be detectable by solar monitoring spacecraft as temporary increases in plasma density and magnetic field fluctuations. Earth's magnetosphere would provide the first line of interaction with any enhanced solar wind resulting from the 3 I/ATLAS encounter. Our planet's magnetic field acts like a shield, deflecting most charged particles around our world, but significant enhancements in solar wind pressure can compress the magnetosphere and inject energetic particles into the radiation belts surrounding Earth. Satellite operations would face the greatest potential impact from these solar weather effects. Enhanced particle radiation could temporarily disrupt satellite communications, affect GPS accuracy, and potentially damage sensitive electronic components on spacecraft operating in Earth orbit. However, these effects would be similar to those produced by moderate solar storms, events that space agencies routinely prepare for through operational protocols and spacecraft design considerations. The power grid infrastructure on Earth's surface would be essentially unaffected by our hypothetical encounter. While extreme solar storms can induce currents in long-distance transmission lines, the disturbances from 3 I/ATLAS's destruction would be far below the threshold needed to create such geomagnetically induced currents. The event would register on magnetometer networks worldwide, but would not threaten electrical infrastructure. Radio communications would experience the most noticeable effects for civilian users. High-frequency radio communications, particularly those used for international broadcasting and amateur radio, can be disrupted by enhanced solar activity as charged particles in Earth's upper atmosphere absorb radio waves. The duration of such disruptions would likely be measured in hours rather than days. Aurora activity would provide the most spectacular visible effect for observers at high latitudes. Enhanced particle precipitation into Earth's atmosphere typically creates more frequent and intense auroral displays, potentially making the northern and southern lights visible at latitudes where they're normally rare. The unique chemistry of particles originating from 3 I/ATLAS might even create unusual auroral colors reflecting the alien composition of our visitor. Commercial aviation would implement standard space weather protocols during the event. Airlines routinely monitor solar activity and adjust flight plans for polar routes when particle radiation levels become elevated. The 3 I/ATLAS encounter would likely trigger similar precautionary measures, with some flights at high latitudes potentially being rerouted to lower altitudes or more equatorial paths. Mars exploration assets would face more significant challenges due to the red planet's lack of a strong magnetic field. Spacecraft in Mars orbit and rovers on the surface rely on their own shielding to protect against particle radiation, and enhanced solar wind activity could temporarily affect their operations. Mission planners would likely implement protective protocols similar to those used during major solar storm events. The outer solar system would experience delayed but potentially more dramatic effects as the enhanced solar wind propagates outward over weeks and months following the encounter. Jupiter's massive magnetosphere would capture and accelerate particles from the event, potentially creating enhanced radiation environments around the gas giant's moons that could affect future mission planning. Some space weather prediction models would be put to their ultimate test by the 3 I/ATLAS encounter. Current forecasting systems are calibrated based on natural solar variability, and the introduction of foreign material into the solar atmosphere would create conditions outside their normal operational parameters. The event would provide valuable data for improving these predictive capabilities. International space weather coordination would play a crucial role in managing the effects of our hypothetical encounter. Organizations like NOAA's Space Weather Prediction Center, the European Space Agency's Space Weather Service Network, and similar agencies worldwide would coordinate observations and forecasts to minimize impacts on technological systems throughout the solar system. The overall assessment suggests that while the 3I/ATLAS encounter would create detectable space weather effects, these would fall within the range of natural solar variability that our technological civilization is already prepared to handle, representing an interesting scientific event rather than a crisis requiring emergency response measures. For observers on our home planet, the hypothetical encounter between 3I/ATLAS and the Sun would unfold as one of the most spectacular astronomical events in recorded history, visible to the naked eye as a temporary brightening of our star, and observable in exquisite detail through telescopes ranging from backyard instruments to professional observatories. The visual drama would play out across multiple days, providing unprecedented opportunities for both scientific study and public engagement with cosmic processes. The initial signs of the encounter would be subtle, detectable only through specialized solar telescopes equipped with hydrogen alpha filters that reveal activity in the Sun's chromosphere. Days before the final destruction, observers would notice a growing bright point moving across the solar disk, initially appearing similar to a large solar flare but maintaining persistent brightness and exhibiting the distinctive spectral signatures of vaporizing cometary material. As 3I/ATLAS penetrates deeper into the solar atmosphere, the visual spectacle would intensify dramatically. Solar observatories worldwide would capture images showing a brilliant tail of plasma streaming behind our visitor, following magnetic field lines in graceful arcs across the solar surface. This tail would be visible in multiple wavelengths simultaneously, creating false color images that reveal the complex chemistry of destruction in unprecedented detail. Amateur astronomers equipped with safe solar viewing equipment would witness history in the making. Specialized solar filters that allow direct observation of the Sun would reveal a bright streak moving across the solar disk over the course of several hours, growing progressively brighter as more of 3I/ATLAS's material vaporizes in the intensifying heat and radiation. The moment of maximum brightness would be visible even to casual observers as a temporary increase in the Sun's overall luminosity. While this brightening would be far too subtle to notice with unprotected eyes, sensitive light meters and properly filtered cameras would record the event as a measurable enhancement in solar output lasting for several hours at peak intensity. Radio astronomy would provide another window into the visual spectacle for observers with appropriate equipment. The destruction of 3I/ATLAS would create radio emissions across a broad range of frequencies, detectable by amateur radio telescopes and providing audio signatures of cosmic destruction that could be converted into sound for dramatic effect during public viewing events. The color variations visible through specialized equipment would tell the scientific story of our visitor's demise. Hydrogen emissions would create brilliant red features, while oxygen would contribute green hues and carbon would add distinctive blue-green coloration. Professional observatories equipped with spectrographs would document these color changes as direct evidence of the alien chemistry being revealed through stellar heating. Planetariums worldwide would undoubtedly create special programs to help the public understand and visualize the encounter. Computer simulations based on real observational data would allow viewers to experience the event from impossible vantage points, following 3I/ATLAS through its final journey, and witnessing the transformation from solid matter to stellar plasma. The photography opportunities would attract astrophotographers from around the globe. Long exposure images through proper solar filters would capture the graceful arc of the plasma tail, while time-lapse sequences would document the evolution of the event over hours and days. These images would become iconic representations of humanity's first observation of an interstellar visitor's complete destruction. Social media would explode with sharing of observations, images, and scientific data as the global astronomy community collaborates in real-time documentation of the event. The hashtags and trending topics would reflect both scientific excitement and popular wonder at witnessing cosmic processes normally hidden from human observation. Educational opportunities would be unprecedented as schools and universities organize special viewing events and incorporate the encounter into astronomy curricula. Students from elementary through graduate levels would have the opportunity to witness textbook physics playing out in real time, creating lasting impressions that could inspire the next generation of scientists and engineers. The aftermath would be almost as visually interesting as the encounter itself, with enhanced auroral activity potentially making the northern and southern lights visible at latitudes where they're rarely seen. Observers in normally aurora-free regions might witness colourful sky displays created by particles from 3I/ATLAS interacting with Earth's magnetosphere. The psychological impact of witnessing such an event would be profound, providing direct visual evidence of the dynamic processes operating throughout the universe and our solar system's place within the larger cosmic environment. For many observers, the encounter would represent their first direct observation of truly cosmic-scale physics in action. The view from Earth would ultimately transform an abstract scientific scenario into a visceral human experience, connecting observers directly to processes operating on stellar scales and providing visual confirmation of humanity's growing understanding of the universe around us. The destruction of 3I/ATLAS in our hypothetical solar encounter serves as a window into cosmic processes that operate throughout the universe, revealing fundamental truths about how stars interact with the interstellar medium and how matter circulates between stellar systems across galactic scales. Understanding these broader implications helps us appreciate that our thought experiment represents not just the fate of one unusual object, but a glimpse into physical processes that have been shaping the galaxy for billions of years. Every star in our galaxy likely experiences periodic encounters with interstellar objects similar to 3I/ATLAS, though most occur too far away and involve objects too small for us to observe directly. The statistical estimates suggest that major stars like our Sun encounter kilometer-sized interstellar objects perhaps once every few thousand years, while smaller debris arrives much more frequently. This means that stellar object interactions represent a continuous background process operating throughout the galaxy's stellar population. The debris ejection mechanisms that created objects like 3I/ATLAS operate in every planetary system during its formation phase. Gravitational interactions with giant planets, stellar encounters, and supernova explosions continuously scatter smaller bodies into interstellar trajectories, creating a vast population of wandering objects that fill the spaces between stars. Our galaxy likely contains trillions of such objects, most too small and distant to detect with current technology. The chemical mixing implications extend far beyond individual stellar encounters. Each time a star captures and destroys interstellar material, it incorporates alien chemistry into its outer layers, gradually mixing the chemical signatures of different stellar systems throughout the galaxy. This process operates over geological timescales, slowly homogenizing the chemical composition of stellar atmospheres and contributing to the overall chemical evolution of our galaxy. The energy scales we've explored in our 3I/ATLAS scenario operate throughout the universe wherever matter encounters stellar environments. Similar physics governs how material falls into white dwarfs, neutron stars, and black holes, though the energy densities and destruction mechanisms vary dramatically. Understanding stellar encounters with normal matter provides insight into more exotic scenarios, involving compact objects and extreme gravitational fields. The spectroscopic techniques demonstrated by our hypothetical encounter have applications extending throughout observational astronomy. The same physical processes that would reveal 3I/ATLAS's alien chemistry operate when we observe the spectra of distant stars, galaxies, and nebulae. Each absorption line and emission feature tells stories about chemical composition, physical conditions, and nuclear processes operating across cosmic distances. The magnetic field interactions we've described play crucial roles in stellar evolution and galactic dynamics. The mechanisms that would guide plasma from 3I/A TLAS along solar magnetic field lines operate throughout the universe, governing how matter and energy flow within stellar atmospheres, between stars, and throughout galactic magnetic fields that extend across hundreds of light years. The isotopic archaeology revealed by our visitor's destruction provides a template for understanding chemical evolution throughout cosmic history. The nuclear processes that created distinctive isotopic signatures in 3I/ATLAS's birth system operate in every star, creating the chemical elements that eventually form planets, moons, and potentially life itself. Each stellar encounter provides opportunities to study these processes directly. The plasma physics demonstrated during our hypothetical encounter governs phenomena throughout the universe, from solar-wind interactions to the behavior of intergalactic gas. The same fundamental equations that describe 3I/ATLAS's transformation into stellar plasma apply to environments ranging from planetary magnetospheres to the hot gas between galaxy clusters. The observational techniques required to study our encounter push astronomical instrumentation to its limits, driving technological developments that benefit multiple fields of research. The spectroscopic precision needed to analyze alien chemistry, the temporal resolution required to track rapid plasma processes, and the coordination necessary for multi-wavelength observations all contribute to advancing astronomical capabilities. The frequency of interstellar visitor detection continues increasing as survey technology improves, with facilities like the Vera Rubin Observatory expected to discover dozens of such objects annually within the next decade. Each new discovery provides additional data points for understanding the galactic population of wandering objects and their potential for scientific study through various encounter scenarios. The theoretical frameworks developed to understand stellar object interactions apply broadly to astrophysical scenarios throughout the universe. The mathematical models that predict plasma behavior, chemical reactions, and energy transport during our hypothetical encounter provide tools for interpreting observations of similar processes occurring around other stars and in other galaxies. Our exploration of 3I/ATLAS's hypothetical fate ultimately reveals the interconnected nature of cosmic processes, demonstrating how individual events reflect universal physical principles operating across all scales of space and time throughout the observable universe. As our journey through the hypothetical destruction of 3I/ATLAS in the solar furnace comes to a close, we must return to the fundamental truth that guided our entire exploration. This dramatic encounter will never actually occur. The real 3I/ATLAS follows a trajectory that carries it safely through our solar system, passing no closer to the Sun than roughly 1.4 astronomical units, approximately the distance between Earth and Mars. This distinction between scientific thought experiment and physical reality is crucial for understanding both the value of our exploration and the proper interpretation of its conclusions. Thought experiments have a long and distinguished history in science, providing tools for investigating physical processes under conditions that may be impossible or impractical to create in laboratory settings or observe directly in nature. Einstein's famous thought experiments about riding on light beams or falling freely in elevators led to revolutionary insights about space, time, and gravity that eventually enabled technologies from GPS satellites to nuclear power. Similarly, our mental journey with 3I/ATLAS has provided insights into stellar physics, plasma processes, and chemical analysis techniques that apply broadly throughout astronomy and astrophysics. The real trajectory of 3I/ATLAS tells its own fascinating story of interstellar wandering and the physics of hyperbolic orbits. As it continues its passage through our solar system, this visitor carries chemical signatures from another stellar environment, preserved in ice that has remained largely unchanged during millions of years of travel through the cosmic deep. The scientific value of studying actual interstellar visitors like 3I/ATLAS extends far beyond the dramatic scenarios we've explored together. Each such object provides direct samples of material from other star systems, offering opportunities to study planetary formation processes, stellar nucleosynthesis, and galactic chemical evolution through analysis of real physical specimens rather than theoretical scenarios. The observational campaigns studying the real 3I/ATLAS have already advanced our understanding of comet chemistry, interstellar object populations, and the survival mechanisms that allow small bodies to endure million-year journeys through space. These discoveries contribute to a growing database of information about the galaxy's population of wandering objects and their scientific significance. The safety of 3I/ATLAS's actual trajectory ensures that we can study this interstellar visitor without any concerns about solar system stability or threats to Earth. The object will complete its passage through our cosmic neighborhood and continue its journey into the galaxy, carrying with it whatever secrets we were unable to extract during our brief opportunity for observation. The techniques and instruments we've described for observing our hypothetical solar encounter are real capabilities that astronomers use to study actual solar phenomena. Solar observatories like the Parker Solar Probe and Solar Dynamics Observatory routinely observe the destruction of small objects in the solar atmosphere, providing ongoing opportunities to study the physics we've explored theoretically. The statistical likelihood of similar encounters involving other interstellar visitors remains non-zero, though extremely small for any given object. The galaxy likely contains billions of wandering objects ejected from their birth systems, and occasionally these cosmic nomads do encounter stars during their journeys through space. Our exploration provides a framework for understanding such rare events when they occur. The educational value of thought experiments extends beyond their immediate scientific applications to demonstrate the power of scientific reasoning and mathematical modeling. By following logical chains of cause and effect through complex physical scenarios, we develop intuitive understanding of processes that would otherwise remain abstract and disconnected from human experience. The boundary between speculation and observation in astronomy often blurs as new discoveries challenge existing theoretical frameworks. Today's thought experiment may become tomorrow's observational reality as our instruments become more sensitive and our survey capabilities expand to encompass larger volumes of space and longer timeframes. The real 3I/ATLAS will eventually fade from observational reach as it continues its journey toward interstellar space, but the scientific insights gained from studying this visitor will continue advancing our understanding of cosmic processes for years to come. Each interstellar object discovery builds upon previous knowledge while potentially revealing new categories of phenomena that require expanded theoretical frameworks. Our exploration serves as both scientific education and preparation for future discoveries that may prove even more challenging to our current understanding of physics and chemistry operating in cosmic environments. As we conclude our journey through the hypothetical destruction of 3I/ATLAS in our Sun's nuclear embrace, we find ourselves with a profoundly altered perspective on the scales, energies, and processes that govern our cosmic environment. This mental voyage has revealed not only the physics of stellar encounters, but also the remarkable position our civilization occupies in understanding and interpreting the universe around us. The true 3I/ATLAS continues its ancient journey through our solar system, carrying within its frozen structure the chemical legacy of a star system that may no longer exist. This interstellar wanderer represents more than just an unusual comet. It embodies the connectivity that links stellar systems across vast distances and enormous spans of time. Every atom within its structure was forged in the nuclear furnace of another star, dispersed through space by processes we can only imagine, and reassembled into the object we observe today. Our ability to detect, track, and analyze such visitors represents one of humanity's greatest intellectual achievements. Less than a century ago, the very existence of other star systems remained theoretical. Today, we routinely discover objects that originated around distant stars, analyze their chemical composition in detail, and use them to understand physical processes operating throughout the galaxy. The scales revealed by our exploration challenge every aspect of human intuition about space and time. 3. I/ATLAS has been traveling through the cosmic dark for periods that exceed the entire history of complex life on Earth, covering distances so vast that light itself requires years to traverse them. Yet our instruments can detect its presence, measure its composition, and predict its future trajectory with mathematical precision. The energy scales involved in stellar processes dwarf every aspect of human technology, while simultaneously providing the foundation for our existence. The Sun's continuous nuclear burning, which would barely notice the complete vaporization of objects as large as 3 I/ATLAS, creates the stable energy flow that has sustained life on Earth for billions of years and will continue to do so for billions more. The chemical complexity revealed by interstellar visitors like 3 I/ATLAS demonstrates the universal nature of physical and chemical processes, while simultaneously showing the incredible diversity of environments that exist throughout the galaxy. The same laws of physics that govern chemistry in terrestrial laboratories operate around distant stars, yet produce compositions and structures unknown in our solar system. The connectivity implied by objects like 3 I/ATLAS suggests that our solar system exists within a vast galactic ecosystem where matter, energy, and potentially even the chemical precursors to life circulate between stellar systems over cosmic timescales. We are not isolated inhabitants of a single star system, but participants in galactic processes that operate on scales beyond human comprehension. The observational capabilities that allow us to study interstellar visitors represent remarkable extensions of human sensory experience. Through instruments and techniques that would seem magical to previous generations, we can analyze the chemical composition of objects formed around other stars, measure their internal structure, and even infer the properties of stellar systems we will never visit directly. The theoretical frameworks we use to interpret these observations demonstrate the power of mathematical description to reveal underlying physical reality. The equations that govern plasma physics, thermodynamics, and nuclear reactions operate consistently throughout the universe, allowing us to understand processes occurring under conditions impossible to replicate on Earth. The collaborative nature of modern astronomy, demonstrated by the global efforts to study objects like 3 I/ATLAS, shows how scientific understanding advances through international cooperation and shared knowledge. No single nation or institution possesses all the capabilities needed to fully understand cosmic phenomena, but working together, we can achieve insights impossible through individual efforts. The historical context of our current capabilities reveals the accelerating pace of astronomical discovery. Each decade brings new surveys, improved instruments, and expanded theoretical understanding that dramatically increases our ability to detect and analyze cosmic phenomena. The study of interstellar visitors has transformed from impossible to routine within a single human generation. The future promises even more remarkable discoveries as our observational capabilities continue expanding. Upcoming facilities will detect interstellar visitors years before they reach the inner solar system, providing extended opportunities for study and potentially even direct encounters with spacecraft designed for such missions. Perhaps most importantly, our exploration reveals humanity's unique position as conscious observers, capable of understanding cosmic processes through scientific investigation. We exist at a remarkable moment in cosmic history, when intelligent life has developed the tools needed to comprehend the universe's fundamental workings, while remaining young enough to find wonder in each new discovery. The real 3 I/ATLAS continues its journey into the cosmic night, but our understanding of what it represents for science and human knowledge will endure, preparing us for future encounters with messengers from distant stars.